Hi, my name is Jeff Hammond, and today I'll be talking to you about the NVIDIA HPC software development kit for the ARM ecosystem. Just to briefly introduce myself, I joined NVIDIA in 2021, and I'm a member of our HPC software team. I focus on ARM CPUs and HPC, as well as Fortran, although like everybody here, I also work on GPU stuff. I've been around HPC for a while, done a wide range of things, MPI, scientific computing, linear algebra, supercomputer architecture. I am a chemist by training, and I've been working on NWChem, which is a well-known open source chemistry code, for more than 15 years, which is relevant because you'll see NWChem stuff later in this talk. And for anybody who's interested, I'm based in Helsinki, Finland. If you want to know more, you can see my GitHub. The motivation for a lot of the things done in my group is that HPC applications need to run across a wide range of platforms, from the developer's laptop to edge devices to CPU-only servers and servers with one or more GPUs. One of the things that we're trying to make possible in our software tools right now is not just to solve a CPU programming problem across a wide range of implementations, or a GPU programming model problem across a wide range of implementations, but a parallel computing problem that spans both architectures. We're trying to build programming models that make HPC application developers successful, whether they use a CPU or a GPU. This is obviously not going to be possible in every single case, but what we'd like is, by default, that programmers can focus on parallel algorithms and then choose their device, and then specialize later if they need to. But what they get out of the box is a parallel computing solution that addresses a wide range of architectures and not just all the CPUs or all the GPUs. For those who might not be familiar, the NVIDIA HPC software development kit includes a wide range of compiler, language, and library support. I'll be focusing on the compilers and the languages here, but libraries are an important part of this ecosystem as well. Obviously, like all processor vendors, we support optimized math libraries for our processors. So you'll see here, obviously, the GPU math libraries that complement, of course, the CPU math libraries that are provided by others. We have a full service communication stack, which includes MPI as well as PGAS libraries, and some optimized collectives and other features specifically for machine learning, like Nickel. And then, of course, there's the programming tools, profilers, and debuggers that complement all these things. Our software tools, the HPC SDK, is available for x86, for ARM, and for Power CPUs. Obviously, it supports our GPUs. Includes C++ and Fortran compilers, includes directive models, the CUDA language family, and all the libraries here. We do more than half a dozen releases a year, and these tools are freely available to you. You can go to that website, you can download them, and you can install them. NVIDIA platforms can be programmed with a wide variety of options. Many people are familiar with CUDA, which is about 15 years old and has been used to program GPUs for maximum performance for many years, but obviously it's focused on GPUs. Since then, the HPC community has developed a number of different options for programming GPUs and other accelerators and CPUs with directives. So starting with OpenACC and OpenMP4, we see that the directive or pragma-based approaches allow developers to mix legacy code with more specialized control for HPC processors. More recently, and what I think is the most interesting, is something that our group has been working very hard on, which is accelerating standard languages. So what this means is taking ISO C++ and ISO Fortran Parallelism, stuff that's the absolute gold standard of portability, can be implemented across a huge range of devices in a non-proprietary way, and take those features and implement them in a high-performance way across CPUs and GPUs. So what I'll be showing in the next couple slides are specific examples where we have successfully deployed the ISO language parallel features on CPUs and GPUs. And of course, in this case, because of this audience, it's ARM CPUs. To give a very specific, simple example of standards-based parallelism, we see here the classic AXB, SAXB, vector addition, whatever you want to call it, algorithm implemented with C++ and Fortran standard parallelism. And what you see here highlighted in green is the only part of this algorithm that has to know anything about parallelism or architecture. and the developer is saying, I have parallel code. There's enough work to do here to justify parallelizing it somewhere, and then the compiler does something with that. Now, obviously, there are cases where this can be abused. If you try to parallelize something that's 100 operations across 1,000 processing elements, that doesn't work. But lots of HPC involves algorithms with significant amounts of parallelism, and HPC application developers are very good at identifying parallelism. And what we'll see next is how well the compiler can do with mapping portable parallel constructs into efficient hardware code. The first example of standard parallelism I'll show is with a code called LULESH. LULESH is a physics simulation code from Lawrence Livermore National Laboratory. It does hydrodynamics. What you see on the left here is the OpenMP CPU implementation. So this is CPU only code. If you wanted to do the same thing with OpenMP on a GPU, you'd have to add a number of extra statements. And what we see here is this code can be transformed into something that's more readable and more compact, and also has less architecture specificity, in the sense that the code on the right you see there represents the transform reduce pattern in C++, which is equivalent to the map reduce pattern many people have heard about. And we see there that we can capture more of the semantics of this algorithm, which is an exact match for transform reduce, and eliminate things like references to get thread ID that were necessary in the CPU code as written to do what this algorithm is doing. So we see here we can have more readable and also more portable code. So this slide is the performance of LULESH with the implementations discussed previously. This is the figure of merit for the 150 problem size, which is, if you've run LULESH, you'll know what that means. The figure of merit, obviously higher is better. So what we see is two different GPU servers. They're both A100 GPUs. One's ARM hosted, one's x86 hosted. And we see 120,000, give or take, figure of merit. This is a bandwidth bound application, so the HBM bandwidth on the GPUs is significant and higher than the DRAM CPU system. So there's a key difference there, obviously, from the hardware. But what is interesting, when we look at the bottom, you see that ISO C++ standard code runs on an A100 GPU. It also runs on an Ampere Ultra Q8030 server and an AMD EPYC 7742 server, which is Rome. And you can see here the performance varies. Now, the red bars are the x86 numbers, and the yellow one is the ARM numbers. So there's a significant advantage there. On the CPU side, that comes from the fact that the ARM CPU is able to drive more bandwidth. I don't know all the microarchitectural reasons, but it's compelling. And we see that also that the NVIDIA HPC compiler stack has a very good implementation of the standard parallelism relative to GCC. Obviously, GCC is optimized for a huge spectrum of problems and doesn't have all the same ability to optimize for HPC applications that we do. But we see here that there's an advantage from the compiler and from the ARM architecture. If you notice, I don't have a GCC number for the ARM server. That is because the GCC implementation of standard parallelism in this case wasn't working correctly, and I didn't want to show something that wasn't meaningful because it's an artifact that will disappear at some point in the future. So, summary, we're running the same ISO C++ code, and it runs really well on a GPU. It runs really well on a CPU, and you can see no code changes. Unlike OpenMP, where the OpenMP code not only doesn't run as fast as the ISO C++ code, but it's also limited exclusively, in this case, to CPU architectures, because GPU OpenMP is not the same as CPU OpenMP. Whereas in this case, with C++, standard parallelism, CPU and GPU parallelism are achieved with the exact same code. Now what I want to show you is some results with Fortran, because it's HPC and Fortran's great, and a lot of people in HPC care a great deal about Fortran. And this is with NWChem. It's with the CCSD parenthesis T algorithm, which is a tensor contraction kernels, very expensive, uses up a lot of cycles for accurate chemical simulations at a lot of supercomputing sites. You can see the code is, the kernels are extracted from NWChem, but they're what NWChem is doing. So I'm going to show two slides. The first one here is just comparing OpenMP CPU behavior and compilers. So there are two comparisons you can observe. One is x86 versus ARM. And we see some nice performance with ARM here versus x86. There's some variation. It depends on the kernel details, the cache sizes, not having specialized this OpenMP code for either microarchitecture. It's going to vary a little bit but based on the fine details. But what you can see is in both cases, the NVIDIA HPC compiler is able to do a much better job with OpenMP on CPUs than GCC. Obviously, GCC is not an HPC compiler stack. They are not focused on providing the best implementation of OpenMP for every CPU. They've got a lot of other problems to solve too. But this is a clear case where the NVIDIA compiler stack is a really good option if you want to be CPU architecture agnostic, because we support x86, we also support ARM, and we support Power. So if you care about running the same compiler on different CPU architectures, the NVIDIA HPC stack gives you a really good option here for OpenMP code. Because one of the important parts of the story I'm telling you today is about getting both CPU and GPU execution with the same code, I want to show you the Fortran standard parallel version of the previous case. So here doesn't have all the details, and in every case, in this case it's an x86 CPU, but it doesn't matter. What matters here is that you can run Fortran standard parallelism, which is blue triangles, and get the same performance as OpenMP and OpenACC. I just didn't include that. You obviously get a benefit from CPU versus GPU. I will also add, of course, performance libraries when you can use them are fantastic. So this case shows, approximately 4 teraflops with the CUDA GPU optimized tensor contraction library, CU tensor. But it also shows that you can write ISO standard parallel code and get a significant fraction. So that's around a teraflop. Now you can say this two different ways. Say 25% of peak is disappointing, but 25% of peak with code that has zero specialization and is completely portable because it's ISO Fortran 2008, 25% of peak is really a fantastic number relative to an expert optimized performance library. So obviously performance libraries won't always exist for every algorithm, and so you want to know, well, what can I get out of portable code? And so this says if you can run portable code with Fortran on a GPU, you could potentially get 25% of the best case scenario for this type of an algorithm. And of course, being able to run that portable Fortran code on a GPU will give you a significant benefit over a CPU, because GPUs are known to have much higher bandwidth and much higher peak floating point capability than any CPU today. Just to complete the story, it's not just the loop code in a custom HPC algorithm that can be accelerated with the NVIDIA HPC compiler stack. We also support the mapping of the mathematical intrinsics of Fortran onto GPUs. So these exist in some cases for CPUs. GCC and iFort both can map the mapmul intrinsic to dgem if you ask it to, or BLAS in general. But this is an important element where if you can map to standard language intrinsics that do linear algebra, you can get really, really fast code on a wide range of platforms, including GPUs, without ever thinking about GPUs, because this is just about taking linear algebra patterns and running them on a device that is capable of running them quickly, whether that's a CPU or a GPU. And you can find the list of all the intrinsics and all the details about this in the link below if you're curious. So to conclude this talk, we know that ISO C++ and ISO Fortran both support a form of language parallelism, as well as intrinsics in the case of Fortran, that can be mapped to a wide range of architectures. And we've shown how, for a C++ application and a Fortran application, we're able to run standard code on CPUs and GPUs. We're able to take advantage of a wide variety of parallel constructs, including libraries, directives, and standard parallelism, all in the same compiler stack, and use the same code everywhere. So I've been doing this for the past few months. I've done it on a Raspberry Pi all the way up to an Ampere Ultra. I've done it on x86. I've done it on ARM. I've done it on GPUs. And you can take the same compiler stack targeting all those different architectures. Obviously, we're very interested in ARM, and we're continuing to build out our compiler stack for ARM CPUs. So if you're a high-performance computing user and you want a Fortran or a C++ or a C compiler that works great on ARM, but also supports the chips you may be using already, and you want to support the same build systems, the same compiler flags, not have to worry about the compiler differences between two different chips, you can use our compiler and take advantage of that. And I'd encourage you to see how this works on ARM today.